Hello, I'll be talking about my joint work with Dominic Scheeder about hard instances for the PPSZ K-set algorithm. Let's start with basic definitions. Let's remind ourselves what the K-set problem is. We are given a KCNF formula, and the task is to decide whether there is an assignment to the variables, which makes the formula true. This is trivially solvable in time 2 to the m, when m is the number of variables. It's NP complete for already k being at least 3. And there are known algorithms which beat this trivial running time of 2 to the n. To understand the exact hardness of this problem, certain hypotheses were developed. The first one is exponential time hypothesis, which rules out running times of the sub-exponential running times, 2 to the little O of n. Strong exponential time hypothesis states that when k grows, the complexity of k-set essentially approaches 2 to the n. So there's no fixed epsilon for which k-sat for any k is solvable in time 2 to the 1 minus epsilon. And indeed, there are the known non-trivial algorithms for k-sat do have running times of this form. So you have some f of k, which deteriorates with k, and you have running time of 2 to the 1 minus fk times n. I would call this epsilon that I've mentioned here the savings. So this would be one way to think of it is as if we are somehow saving on an epsilon fraction of the variables, and we're just doing an exhaustive search on the remaining variables, which is not exactly what happens, but somehow to imagine what this running time represents. The best known savings are 1 over k asymptotically, and this is given by all of these reasonable k-set algorithms. They have different constants in this asymptotic notation, and for a very long time we are stuck with these savings, and so one may wonder that this failure of improving on these 1 over k, it's for a reason. So we can postulate another hypothesis, super strong ETH, which says that basically this 1 over k is the best possible savings you can achieve. So there are no algorithms with savings 1 over little of k. Of course, all these hypotheses are stronger than p, not equal than p, therefore we do not really expect to be able to prove them. Neither do we expect to be able to refute them, at least some of them, very easily. They were formulas in the first place to capture this difficulty. However, the reasonable and achievable thing seems to be to verify them for known algorithms, to show that known non-trivial algorithms have hard instances on which the running time is consistent with either of these hypotheses. And this is what we do for the PPSZ algorithm, which is the best known k-set algorithm, and we actually show that the strongest of these hypotheses holds for it within a certain regime of parameters, but I will get to that later. And it's also important to note that I'm not at all suggesting that this should be considered as an evidence for the truth of this hypothesis. Rather, I think results of this form should somehow guide us on how to find better algorithms. So this just shows limits to our common ways of thinking about k-set. And in fact, the strongest of these hypotheses is most likely false. A very interesting result is due to Vias and Williams, which shows that if our instances are random, we are only looking at random instances of k-set, then actually we can obtain asymptotically better savings, better than 1 over k savings. So let's get to the algorithm. PPSZ stands for its inventors, Baturi, Putlock, and Tseitin Zane. This was a strengthening and extension of an earlier algorithm by them, PPZ, by Baturi, Putlock, and Zane. It has a very simple idea. So you try to randomly produce a satisfying assignment by picking a random variable at a time, and somehow if you see the value of this variable, if somehow it's obvious to you, which I will explain exactly what I mean by that. So you just set it to the w's value, otherwise you pick a random value and continue. This obvious value is decided by an algorithm, a sub-exponential time algorithm, which we call sound heuristic. It takes a formula and a variable, and it outputs 0, 1, or it says I don't know. And the property of is that if it outputs a value, then it means that under any satisfying assignment of this formula, that variable has to have that given value. So in that sense, it's sound. And some examples of this heuristic are, well, the simplest one is arguably unit clause. So if you see a unit clause containing only one literal, then obviously that value is forced. If that formula is satisfiable, any satisfying assignment has to set that value in this fixed way. And this is the heuristic that was used by the PPZ algorithm. We can make it a little bit more sophisticated by looking at the following. So this looks at small sets of clauses which logically enforce value of a variable. And we call the corresponding algorithm coming out this weak PPSZ, and I will explain why. And the stronger version of this, which we call strong PPSZ, is when you can derive the value of a variable with small width resolution. And this small, of course, is a parameter. You can define what you mean by small. So when you produce a satisfying assignment with some probability p, you can repeat such an algorithm 1/p time to get and you get 1/p time algorithm. So what we study in this type of algorithm is the success probability. So let me just briefly mention what is known in this respect. So PPZ algorithm, which looks at this unit clause heuristic, it basically gives 1/k savings, exactly. PPSZ algorithm, which looks at super constant width resolution, it gives C/k savings. As you can see now, the C is bigger than 1. And for some technical reasons, they had to give a different analysis for general case, and it only worked for k at least 5. And this was later taken care of by Hertley, who showed that it works for every k. And indeed, his proof can also show that you can use the weaker heuristic, which just looks at subformulas of a certain size. So the correct way to think about PPSZ is through encodings. So what PPSZ does is really encoding satisfying assignments. We're given a formula, permutation of variables, and satisfying assignment, and we want to produce a bit string of hopefully shorter length, which somehow encodes the satisfying assignment. And you can probably expect how it works. So you process your variables in the order given by the permutation. At every step, if you can see the value of your variable with your heuristic, then you just know it and you skip. So you don't add this to your encoding, and you just restrict the formula, go to the next variable. Otherwise, if the value is not seen by the heuristic, then you add it to your encoding and you restrict. So by this procedure, you are creating this bit string, and it's easy to convince yourself that given this encoding and the permutation and the heuristic and the formula, you can uniquely recover the satisfying assignment. So you can immediately transform this into a k-set algorithm by picking a random bit string and a random permutation of the variables and trying to decode this. Pretend that this is an encoding of a satisfying assignment, so you try to decode it. you can see that it's not difficult to see that the success probability of PPSZ can be written in this form. So, basically the result of PPSZ is that it gives a lower bound for this quantity, which for unique case sets is not so difficult because you can just use Jensen's inequality and just basically reduce the problem to understanding this expected code length. But for general case that is a bit more difficult. But we're interested in upper bounds and what is known about upper bounds. So there are two results from us and our other co-authors. The first one, we gave an upper bound of log squared k over k for strong PPSZ. So this works for resolution. And later with Putlog, we showed this 2 over k, or so this super strong ETH type hard instances, but this only worked for weak PPSZ. For strong PPSZ, we only managed to get rid of one log factor. And in this work, we solved this problem. So we get the same kind of hard instances bound. This instance is a bit different, but now it works for strong PPSZ. So how do we do this? Well, we look at this expression again. We want to upper bound this. So we want to upper bound this sum. It would be useful if we didn't have too many summands. So we will indeed be looking at uniquely satisfiable formula so that we only have to look at one summand. And also this is kind of not particularly pleasant to work with, this upper bounding such an expression, because we don't have Jensen goes the wrong way. So we construct our formula so that under any permutation, this encoding length will be large, and then that will give us the bound. Our instances are coming basically from our previous work, which is from Tseitin Formulas. These are formulas defined on simple graphs and a vertex labeling of this. We have an edge on, we have a variable on each edge, and the constraints are that for every vertex, if you sum mod 2, the edges around this vertex, they add up to the label of that vertex mod 2. And it's easy to see that if the sum of these labels mod 2 is 1, this is unsatisfiable, and indeed this is what this is a very important object in proof complexity. But here we look at the satisfiable instance. We need satisfiable formula, so we just set all the labels to 0. So in particular, the all 0 assignment is a satisfying assignment, but we can also have other satisfying assignments. Note also that if we have a degree k graph, then this will give us a KCNF. So this is how we control this with the initial width. The number of variables is the number of edges, and observe that when we have an encoding, so run this encoding procedure of PPSZ and think about this beta that it produces. So it's a sub-partial assignment of this assignment, and but the fact that it's an encoding, it means that it uniquely forces everything outside. So once you restrict your formula with this sub-partial assignment, then everything else is forced and is uniquely satisfiable. So let's all use this to make an observation, which is very crucial. So if we look at the all 0 assignment and any encoding of this assignment, I claim that the set of edges not appear in the encoding have to be acyclic. And this is for a very simple reasoning, for a very simple reason that if you look at this remaining formula, this is the restricted formula under the encoding. By the definition of an encoding, this should be uniquely satisfiable. But if you have a cycle, and remember that these vertices all have label 0, now we actually have at least two satisfying assignments, the all 0, and you can set everything around cycle to 1. And that is a contradiction. So any encoding of the all 0 assignment can leave at most n-1 edges outside, therefore it has to be quite long. And this is exactly the type of lower bound that we want in our encoding. Of course, the problem is that now we have too many satisfying assignments. and it's not easy to deal with that. So we will make it uniquely satisfiable by applying some modification. So we are basically just throwing some new clauses, which we call bridges, and these are between edges. So we look at clauses, edges which are sufficiently far apart, and we add this not x in or not xe prime for some of these edges. And if they're sufficiently far apart, in particular, if of distance at least half of the girth of the graph, then every cycle should contain at least one such bridge. In fact, many of such bridges. Therefore, you cannot set any bridge to all one. So all cycles have to be set to 0. Therefore, this formula is uniquely satisfiable. And we use this exact formula in our previous paper, and for the weak heuristic, this actually works. So if you have, if you're only looking at small subformulas, this works. But for resolution, it doesn't work. Constant width resolution, well, constant meaning width, depending on the degree of the graph, sees all the values. So the all-zero assignment has basically an encoding of empty, an empty encoding. So we have to do something with that. There are too many bridges. We need to take care of this. So we still somehow follow the same idea. We do throw in some bridges, but we do preserve some kind of internal structure on these bridges. And then we prove that for any small set of edges, that they cannot force any variable or any edge outside of this set in small width resolution. So we need to prove a width lower bound. And for this purpose, we use the very convenient characterization of resolution by Atserias-Dalmau, which is given, we can describe it as a game. Given an unsatisfiable formula f and an integer L, the L-bounded game is defined as follows. Have two players, delayer and prover and delayer, together may attain a partial assignment alpha, which has size at most L, and at every step, prover either erases some part of this alpha or queries a new variable, which is not set. And in this case, the delayer has to assign a value and alpha is updated. And the theorem is that if a delayer can always avoid falsifying the formula, then it means that this formula is not refutable in width L-1. So it means that, what we're going to do is to give a strategy for the delayer in this game. That's some parameters. The delayer really likes to set answer to 0, but the problem is that delayer is already somehow committed to answering 1 on this edge, which is allegedly forced by the encoding. So the delayer is forced to say some 1s. But then the problem is that when you start answering with 1s, at some point you might falsify bridges. So you should be careful with bridges. So it's good if our construction is so that we don't have too many bridges, and also we know exactly where they are so that we can carefully avoid them. And this is what we do. So the core of this construction is somehow coming up with this kind of structure on how to put these bridges. And this is given by graphomorphisms, which just reminding you that this is a mapping from vertex set of a graph G to a vertex set of graph H, which preserves edges. And because of this, you can also think of it as a mapping from edges of G to edges of H. And now our bridges are just, so we put a bridge on two edges which are mapped to the same edge. So E and F are on this, have a bridge between them if they're both mapped to the same edge. It's also clear that if the number of edges in this graph, which would be, you can think of it as the number of colors that each edge is getting, is less than the girth of graph G, then this resulting formula is uniquely satisfiable, because now every cycle should contain two edges of the same color. Therefore, it contains a bridge. Therefore, it's uniquely satisfiable. So we need to pick these G and H carefully. In fact, we will be looking at a little bit more restrictive form of homomorphisms. We're looking at locally injective homomorphisms and also locally bijective. These are homomorphisms which are injective on every neighborhood. And if it's bijective on every neighborhood, you call it bijective. So our result is basically the following, that if you have a graph G with a locally injective homomorphism to another graph H, which has fewer than girth of G many edges, then for any parameter W, which now depends on the girth of this color graph, if we look at this formula, the Tseitin formula on G, and the bridges coming from this homomorphism, then PPSZ with resolution with W has success probability at most this much, and which is precise in the form we want. So we need G and H now. We will be using this result that given to any 2K regular graphs, you can construct another graph, which is essentially locally indistinguishable from both of these graphs. So there's a graph G, which is not too big, and it's mappable to both G0 and G1 by locally bijective homomorphisms. So what we do now is we take G0 and G1 to be both two high girth graphs, but of different sizes. So we have a larger graph on N0 vertices and log N0 girth, and G1 is on log N0 vertices and log N0 girth, and then G is basically given by this theorem. And our formula is basically the Tseitin formula in this graph and the homomorphism to G1. So how does the proof work? We look at, again, we assume that we have a small set of edges which force everything else, meaning that there's a large set of edges remaining. We first find an expander inside these remaining edges. And this is just more or less the usual of expansion that we call expand AB expander if every set of A vertices has B edges leaving this set. So we set all other edges to 0 and just focus on this expanding subgraph. And our result says that so if we have such an expander which is mapped with a locally injective homomorphism to another graph H, then we cannot derive any single edge in small width when there is some relation between these parameters and the girth of this color graph. The strategy of the delayer can be described as so basically the delayer needs to answer some edges to 1 and some to 0, and the problematic ones are the ones. So somehow the delayer maintains some vertex disjoint paths. These paths represent more or less the safe edges when he can answer to 1. So in particular, we guarantee that there are no bridges on these paths, nor between these paths. And so this middle section of these paths will be the safe part. And the edges which are not on these paths will be just 0, just answer 0. But the edges in these paths need some care. So just to represent it a little bit more clearly, so if you have these two disjoint paths, this middle section, this is the section which is safe to answer 1, and we guarantee that there are no bridges between these paths, neither on the paths themselves, but but maybe there is an edge which is queried on the end sections. In this case, we will be updating our paths, and this is done via taking some of these branches instead and possibly shortening the path and so on. But because of this, we also want to guarantee that there are not too many bridges between a path and the branches of another path. So when we do this modification of the path, then we'll see whether it lies in the middle section of the path or it's outside of a path, in which case we will answer 0. Of course, the details are in the paper, which hopefully you'll read. So the result is that, just reminding them, our main result is that the best savings we can get from PPSZ algorithm when you allow resolution with around square root log n of the variables, you get super strong ETH type savings only. There is still a gap between this precise constant. So the lower bound of PPSZ gives pi squared over 6, but we get something like 2, and it's not clear what is the correct constant, and it seems to be a very difficult question, but absolutely worth studying. It's not clear either what is the savings of randomly lost PPSZ, so that would also be interesting to understand. One can also ask whether changing the heuristic will really make this algorithm more powerful. This is also not so much studied. And the last question is whether these extremely hard instances for an algorithm actually tell us anything about finding new algorithms. So this is also something one should think about. So that's it. I hope you'll read the paper. Thank you very much.